In the previous video, we discussed how to locate vertical asymptotes for a rational function. Vertical asymptotes are also known as non-removable discontinuities. However, another type of discontinuity or break in the graph of a rational function is possible. This is called a hole. Now, a hole is exactly what you would imagine it to be. It's going to be as if someone plucked a single point out of the curve, leaving a hole behind in its place. So what causes a hole to occur in a rational function? Here's the definition. If a common factor can be divided out from a rational function, then a hole exists at the zero of that factor. Now don't panic, we'll do some examples to illustrate that definition. But for now, you'll want to know holes are also known as removable discontinuities. So a vertical asymptote is a non-removable discontinuity. A hole is a removable discontinuity. One way to remember that is I'm basically removing a single point from the graph of the function, leaving a hole behind. Let's consider example 3. The following graph has a vertical asymptote at x equals 1 and a hole at ordered pair 2, 3. So looking at the graph, you can see the vertical asymptote here at x equals 1. You can also see that there's a single point removed or a hole in the graph located at ordered pair 2, 3. Factor the numerator and denominator of the given rational function to observe the difference between how a vertical asymptote and a hole is formed. So f of x gives us the equation of the graph. It's the ratio of two quadratic polynomials. So in order to examine the difference between the vertical asymptote and the hole, we need the constituent factors of both the numerator and the denominator. So observe, the numerator would factor as x plus 1 times x minus 2, and the denominator would factor as x minus 1 times x minus 2. Because there's two factors in the denominator, we can see that we're going to have two restricted values. Looking at our first factor, the zero of that factor is x equals 1, so we have to throw 1 out of the domain. From the second factor, we can see the restricted value there is 2. Putting these together on a number line, we can describe the domain as negative infinity to 1, union 1 to 2, union 2 to infinity. So how does this domain relate to the graph? Well, the left branch of the graph has x values from negative infinity up to, but not including 2. Oh, I'm sorry, not including 1. At x equals 1, we have our vertical asymptote. Then, between the vertical asymptote and the hole, that is between the interval from 1 to 2, we've got defined or solid points on the graph, and then to the right of that hole, from 2 to infinity, we've got the rest of the graph. So what causes the hole and what causes the vertical asymptote? So going back to the factored form of our function, notice we have the common factor x minus 2 in the numerator and the denominator. So we can divide out or cancel that factor. Notice we are actually removing that factor. And the zero of that factor that we're removing is 2. So notice the zero of the removable factor is the x value of our hole. So the factor that we remove goes with this point that we remove. The reduced fraction is x plus 1 over x minus 1. Now we still have a factor in the denominator that we cannot remove. This is non-removable. The zero of that factor is x equals 1, and that corresponds to the equation of our vertical asymptote. So if you can cancel out or remove a common factor, that gives rise to a hole, or a single point that's been removed from the graph. If you cannot cancel a factor from the denominator, it is non-removable, and that corresponds to the x value, or the equation of the vertical asymptote. Okay, we better practice that again to keep all of those details straight. So let's take a look at example 4. Locate the vertical asymptote and the hole for the rational function h of x. Write the equation of the vertical asymptote as a whole of the vertical asymptote and express the whole as an ordered pair. So we have the function h of x, and we want to write it in factored form. So the top, we have the factor x minus 4. The denominator is the difference of two squares, which we could factor as x plus 4 times x minus 4. So notice we have two factors in the denominator. So at this point, we have two restricted values. From the first factor, we can see x cannot be equal to negative 4. And from the second factor, x cannot be equal to 4. For good practice, we can express the domain of this function as negative infinity to negative 4, union negative 4 to 4, union 4 to infinity. Now, taking a look at the factorization of our rational function, we observe there's the common factor x minus 4 in the numerator and the denominator. So we can divide it out, we can cancel it out. Notice we are removing that factor. After canceling that factor, the reduced rational function would look like 1 over x plus 4. There's still a factor in the denominator that gives rise to a restrictive value, but it was non-removable. I can't cancel it out. So from our removable factor, the 0 of that factor was 4. That's the x value of the whole. So the whole is going to occur when x is equal to 4. Now, I got to figure out how to find the y value of that whole. What's the actual location on the graph? The way that we're going to find that y value is by plugging our x value into our reduced function. So if we plug 4 in for x, we would get 1 over 4 plus 4, or 1 over 8. So a whole occurs at ordered pair 4 and 1/8. So again, pay attention to that process. That's going to be something that's easy to forget. How do you find the y value of the whole? Reduce your function and then plug in the x value to that reduced function. The resulting output is the y value of the whole. Also, we have a vertical asymptote. I'm just going to call it VA at the 0 of our non-removable factor, which would be x equals negative 4. So if you can remove the factor, that leads to a removable discontinuity or a whole. If you cannot remove the factor, again, we call that a non-removable discontinuity. That leaves behind a permanent boundary line in the graph or a vertical asymptote.